Hello, everyone. My name is Zhe Yu. I'm an assistant professor in the Department of Software Engineering at RIT. Today, I will be presenting our journal first paper from TSE. And this paper is about identifying self-admitted technical debts with Jitterbug. And the self-admitted technical debts is a specific type of technical debts which were self-admitted by the developers who introduced them. So that's why from the code comments, we can usually directly identify those SATDs. So here are some example comments that are associated with these SATDs. And in our work, we divide these SATDs into two types. The first type is called the easy to find SATDs, and those are the ones which can be automatically identified without human verification in almost 100% precision. And those SATDs also always contain keywords like fix me or to do. So if you see these keywords, then it is almost always related to an SATD, right? And the second type of SATD, we call that hard to find ones. And those are the SATDs which only human experts can accurately decide whether they are SATDs or not. And an example comment is this line. And a human can easily decide that this should be associated to an SATD, but it is not an easy task for a machine learning model to predict. So the most important message this talk wants to convey is that given these two types of SATDs, we should not waste too much effort on finding the easy to find ones. Instead, we should focus more on identifying the hard to find SATDs. Right. So we propose a framework called Jitterbug, which takes two steps to identify the SATDs. And in step one, it automatically identifies the patterns that can predict for SATDs in close to 100% precision, so that there is no human verification required for this step. And in step two, we want to find the rest of the SATDs, and those SATDs are hard to find. So every identified SATD here requires human verification, and that's why we use a strategy of human in the loop information retrieval to find those hard to find SATDs. So here we show the overall workflow for Jitterbug, and we have some training data from some software projects, usually like a project 1 to K. And we also have some test data, which from a different software project K+1. For step one, we will learn the patterns from the training data, which can predict these SATDs in close to 100% precision. And then we will apply this pattern to filter the test data, right? So for the code comments, which contain the pattern, we will directly output them as the SATDs in like almost 100% confidence. And for those comments which do not have the corresponding patterns, those will form the unlabeled data for step two, right? And in step two, we train a machine learning model in our training data and to predict on the unlabeled comments, right? The code comments which does not have the patterns. And then we select the comments which has the highest prediction probability from this machine learning model, and then show these selected comments to a human experts. And these human experts will decide for each of these comments if it is a SATD or not. Right? And these human decisions will then also be utilized to retrain or update this machine learning model so that it can be better adapted to this target project, right? And make more accurate predictions. And then this model will be used to select the next batch of comments showing to the human experts. So this step will iterate until most of the hard to find SATDs were already identified by these human experts. We also utilize an estimation algorithm to estimate the number of SATDs remaining in these unlabeled comments so that we will be able to know when should we stop this process. So then let's take a closer look at each of these steps. In step one, we utilize this following finish function to identify the patterns for easy to find SATDs. So this finish function is the precision of the pattern P to the power of 4 times the support of this pattern P. So this means this finish function means that Mostly we favor a high precision, right? But we also require this pattern to be not too rare, right? Say, for example, if there is one pattern appearing only once but has 100% precision, we still do not think this is a very useful pattern, right? So using this finite function on the dataset originally collected by Maldonado and Shihab in 2015, we identified these following 4 patterns. Here in this work, we only considered one term, like one term as pattern. We didn't consider more complicated scenario as like 2 gram or n gram. But in the future, we can do that. So for these 4 identified patterns, in the labeled data, training data, we found that the precisions are quite high, but not as high as we expected. So we then go to manually verify the conflicting comments, which were labeled as non-SATDs in the original dataset, but were predicted by these patterns as actually SATDs. So the result is quite surprising. Among the more than 300 verified code comments, most of those should actually belong to SATDs. Only 8 of these are not, right? So that means most of these code comments were wrongly labeled in the original dataset by some human experts, but they were correctly predicted by these patterns. So then we change those labels and apply these 4 patterns again. And in this time, we find that the precisions are almost always close to 100% for every dataset, for every software project. And also the recall for these projects sometimes are quite high. And that also suggests that also shows the reason why some existing machine learning algorithm performs very good on predicting these self-admitted SATDs, on these self-admitted technical debts. That's because these easy to find SATDs, they consist of a large portion of these SATDs, right? And they are really easy to identify, like close to 100% precision. So that's why we should actually, if we remove these easy to find SATDs, and for the hard to find ones, the machine learning models are not performing very well. So for the rest of these hard to find SATDs, we have run some experiments, a cross-project prediction experiment for some supervised learning algorithms on the rest of the hard to find SATDs. And here we plot their precision at 10 results. So the reason why we show this precision at 10 is because those are the top 10 predictions by each of these classifiers, right? So those should be the most confident predictions. And this precision at 10 results suggest that even for these most confident predictions, these machine learning models cannot achieve a reliably high precision across all these projects. So that means this is predicting for these hard to find SATDs is a very difficult task for supervised learning. And second is that we definitely need human verifications, right? So that's why we utilize this human in the loop information retrieval process to identify these hard to find SATDs. And our results show that if we target for 90% recall with our estimation, and the random forest classifier performs the best, and it can achieve around 90% recall in every software project with around 20% cost. And this 20% cost means that the human experts needs to review 20% of all the code comments, right, to identify 90% of the SATDs, the hard to find SATDs. And this is a huge saving in terms of effort if you compare it against 100% cost. However, 20% cost is still a very large amount of human labor, right? So there is still room to improve. So overall, our take-home message is that for future research on identifying SATDs, we should focus more. We should focus more on identifying the hard-to-find ones, and that means we should filter out these easy-to-find SATDs first, and then try to improve the performance on the hard-to-find ones. Okay, thank you. Any questions?
And we are live. Do I see any questions from the audience? No, not so far. As I wait for them, I read your paper, very interesting.
Thank
I
you.
was wondering, how is this different from the standard active learning approach, where you just select items on a decision boundary and then the human evaluates them? Is there a difference, or is there not? The
So,
paper wasn't very clear about it.
okay.
Yeah.
So, to answer that question is it's actually like two parts. Like first of all, our approach is kind of a two-step approach. So the first step is has nothing to do with active learning. It's just
Mm-hmm.
like detecting some patterns, so that those patterns has almost 100% precision to identify these SATDs. For example, if that um, comment contains some keyword like to do or like fix me, right?
Mm-hmm.
So that's the first part. And for the second part is quite similar to active learning. However, the goal is not exactly the same as active learning, because for active learning, our goal is to learn a better model, like
Mm-hmm.
uh, with fewer training examples as possible, right? So that's the goal
Mm-hmm.
of active learning. However, for our problem, it's more like an information retrieval problem. So the goal is not to learn a better, like we do need a better model, but the ultimate goal is not to have that model in our hand. The ultimate goal is to kind of retrieve like find the technical debts as soon as possible, right? Without like having humans to say manually read too many comments. So that's the ultimate goal of our problem. So in terms of the difference for active learning, we can focus on the uncertain part, right? Like which examples will help our like improve our model the most. But for our problem, we need to focus on two different parts. Like the first is the same as active learning. We want to improve our model as soon as possible. However, we also need to kind of use something like certainty sampling. Like we just sample the most certain like suggestions from our model. So that's our it is more likely that those will be technical debts. So our human will not waste effort on the ones which are like less confident, right?
Mm-hmm.
So that's a
But is
difference.
but isn't that the same as in active learning, where those to do and fix me's would be far away from the decision boundary and sort of
Yeah, but
real?
yeah, but the to do and those we use a different way, because another thing is that like we found that all the existing papers, they report this F1 score and everything like precision recall with those we call easy to find SATDs. But
Oh.
it is actually those easy to find SATDs actually covers around 50% of the SATDs, and those are really, really easy to find. Like we can use some very simple rules to just find out those SATDs. So we think it's not a good thing that we incorporate those in our like performance evaluation, because it is hard to see which algorithm performs like better if we just incorporate those. And those are and we don't want our model to focus on identifying those easy ones. So we just
Yeah.
say rule out the easy ones first, and then we train our model to specifically focus on the hard ones. So that's
Okay.
the
Yeah.
strategy.
Okay. Yeah. I agree. I totally agree. Now we have a question from the audience. Do you consider comments from issue tracking or commit message, or is it only code comments?
Yeah, so right now we only we have only work on the publicly available data set. So we have not considered other source of this like SATD, but uh, I I we haven't looked into this issue tracking systems, but we think it's should be quite similar as long as the message itself is just like similar, like natural language. Maybe for the easy step, we will identify some different patterns, like for different source of information. But the strategy might be like applicable, but we haven't tried that yet. And we just work on this widely applied data set provided in 2015. And during our study, we actually found another interesting thing, which is that there are many comments were not correctly, like we think were not correctly labeled because it contains some very obvious patterns, like to do and fix me. And when we manually read those, we think it's definitely should be considered as technical debts. But in the original data set, they were not labeled as technical debts. And they mentioned that those data sets were labeled all by humans manually. So like for those easy to find ones, we like our claim is that the easy pattern recognition solution is even more precise or like than the human annotators.
Yeah, I mean, I realized that there are mistakes in the original datasets. My students have also complained me about this. But the question is, did you update the dataset, or is
We
there a new
have
dataset
an
somewhere?
updated version on our GitHub repository. Like I think that link is in the paper. But one thing worth mentioning is that we only updated the ones we see easy to find patterns. So we have we didn't manually reviewed all the comments in the original dataset and correct everything. We just find conflicts between our like easy to find SATDs identified by our patterns and the like the original labels. Like we checked the conflicts and we found 99% case is like our labels are correct than the original one. So we updated that portion. But for the comments like which do not have the easy to find patterns, we didn't touch that.
Okay, that's good to know. Then the question, can you, from Sridaha Slimakonda, can you clarify how do you decide the edge of the boundary, whether the same is inside or outside? What factors do you consider to decide that?
Actually, I'm not very clear. What do you mean by the edge of the boundary? Whether the same inside or outside, what factor do you consider to decide that? Can you just clarify a little bit on what do you mean by the edge of the boundary?
Yeah, I don't understand any better either. So
yeah, maybe you can continue that in the discussion.
Find the space boundary, like how do you find the border between the classes, which you do with SVM, right?
Oh, if the boundary means that like the decision plane of the kind of decision plane of a support vector machine, like what instances we will predict as SATDs and what we will not predict as SATDs. To be honest, in our paper, for the easy part is pretty clear, right? Like if the comment contains the pattern, then it is predicted as SATD with almost 100% precision. So that part is pretty clear. But for the hard part, what we found is that it is really not an easy task to automatically rely on the prediction of the machine learning model. So what we did is that we just rank all the comments by our predictions for whether it can be will be SATD or not, and we will ask the human like this is a simulation, but we will ask some humans, to just
yes, you have 5 seconds. So I invite everyone to the next to the discussion group.